64. Oh, don't look. Yeah, I already got started. Let's erase it. I already had that worked out as leftover. Leftover from last year. All right, so here's what's going on with 64. You've got this function j is equal to this, and it's got two unknowns, a and k. So we worked that example yesterday where we had to find the k. Well, this time, and we had what? We had like a 20 here, I think, didn't we? We had a 20 in front of there. This time, you've got two unknowns. Well, if you have two unknowns, then it takes two, these are what will become known to us as initial conditions, right? Two values of the function we need to know so we can figure out what those are. So if you have two unknowns, you're going to need to have two pieces of information to figure that out. So what you do is you take the first one, you plug it in. So you plug a 1 in for x. So that gives you a e to the k times 1, and that's got to equal 5. And then you plug in a 3, a e to the k times 3, and that's got to equal 10. Now I would rewrite this. Normally I would just have written that like this, and this one I would just write a e to the 3k. Okay, and then it's just algebra 1 thing. It's just an algebra 1, algebra 2 thing, which is two equations, two unknowns. And the most common technique, or one of the techniques for that, is substitution. It's just substitution. So all you need to do is, I would say I would divide by e to the k over here on this one. This would be pretty simple. And I get a over e to the k. Now what can I do with that? Oh wait, I just did something wrong. Not a. 5 over e to the k. And now what can I do with that? Put that right there for that a. Okay. So we got 10 equals 5 over e to the k times e to the 3k. Now what can you do with that? Awesome. Good. That is exactly what you do when you have, this is just the old base of the same, powers you're dividing, you do what with the exponents? Subtract the exponents. So this is 10 equals 5e to the 2k. Right? 2k. And then now it's just like the problem we had yesterday. Now you divide by 5, so you get 2 equals e to the 2k. Right now, as I'm looking at this, as I'm going, one of the things I noticed, and it's pretty typical, but as I'm going around, just for future reference here, as I'm going around looking at your homework, I'm looking at a problem like 64. I'm not seeing a lot of this work on some of your papers, right? So which I think you kind of have to have. So if you've got questions, if you're not sure, I'm glad you asked about this one, because we probably need to talk about it. Okay, now, do the ln of both sides is kind of what I said yesterday. That's just going to equal 2k, right? If I do the ln of this side, once you do that a couple times, you're like, oh, yeah, do the ln of ln e to the 2k, that's just 2k, right? They just kind of cancel each other out there. So that's 2k, and then divide by 2. So we get k equals, I'm going to go to the next page here, but we get k equals 1/2 ln 2. Now, yesterday what I did is I put that 1/2 inside there, but I don't think that gives us any advantage on this one, so I would just leave it like that. Okay, 1/2 ln 2. Now, what do we have to do with that? Plug it where? There, right? And then that'll tell us what A is. Okay, so, oops. 5 over, what was it, e to the k? So that's 1/2 ln 2 equals A, right? Now it might be to our advantage to put that 1/2 up in there, right? Because now we would have 5 over, in some cases, I wouldn't even mind if you just left like this, but I think as a habit, if it can simplify fairly nicely, we would rather do this. Wouldn't that be square root of 2? Bring the 1/2 up in there, that'd be square root of 2. What's e to the ln square root of 2? That's just square root of 2. So this is 5 over square root of 2, which again, I'm okay with that, but you guys probably would remember doing this, right? Root 2, root 2. So it'd be 5 root 2 over 2. So at the end of the day, we've got the j function. Now, what did they want? They just wanted to find j of x. Was that it? They just wanted a and k? Then we got it, right? So, but a lot of times, problem is, well now we would do this, we'd say, okay, that's A e to the 1/2 ln2, ln2 x, right? So that's k, so I put in my a and my k. Now I've got my j function. Now I can do some other stuff, like I can find j of 3 or j of 7, or, you know, and then I could plug in a 7 or find some values that they wanted to indicate. All right, good. Anything else on Appendix E? That was our last one on Appendix E.
That's 66.
66. You want to look at that one? Look at that one. I've got it. Actually, I got it worked out here. Okay. So this is just a matter of do the log of both sides. That's what I would recommend. Then you can bring the x plus 3 down. ln e is just 1. So now you get that. So you get x equals that. Is that all they wanted you to do on 66? Solve for x. Okay. Appendix G. You with that? No others on Appendix E. Now, Emily, you had some, but we kind of talked about those, right? So that was good. Nobody else had any? Appendix E. Okay. I'm trying. I had a couple on here, and I didn't know. Let's see. Well, that was the one we did in class, 58. What about this section here? That, Emily, that's what you and I just talked about. 52, 54.
Yes.
Right? What'd you guys do? Tell me what you guys did here, because sometimes you guys will do it differently than I would have, and it might be even better.
Square root.
So you on 52, what?
Oh, I switched to x.
Switch what to exponential form? This one?
Should be 4.
So this is what they gave you. So 4 to the 2.1 is equal to a. Right? I would agree with that. And then what'd you do? What'd you do from there?
I don't know. I have to work. I just don't know what it means.
What'd you do next?
I don't remember. I did that first.
Zach, what'd you do on 52?
Basically,
Of this one?
to the x equals
Like that? And how? How did you solve for x? Or the box? Oh, because they're both equal to a. So 2 to the box equals 4 to the 2.1. Right? And then what? Yeah, I like this. This is good. Right. There you go. That's what I was looking for. 2 is the same as 2 squared. Right? 4 is the same as 2 squared, right? And then what can you do when you have power and power? Multiply. So that'd be 2 to the 4.2. Right? So what's the box equal? 5.2. Now that's one way to do it. Okay? There'd be several things we could do here to understand this. Yes, that's Jesse, what'd you do?
So I had log 2 of a.
Right.
And then I plugged in 4 to the 2.1 and for a.
So you took this. Yeah, that's where I thought you were going with it. So right here, you basically solved for a. So then you took this and put it right there.
Yeah.
So now you got log base 2 of 4 to the 2.1. Now what can you do with, I like this. And then what can you do with that? You can bring the 2.1 down, right? So now you got the 2.1 down here, times log base 2 of 4. Now what's log base 2 of 4? That's just 2, right? 2 raised to the what makes 4? 2 raised to the 2. So this is just 2. So now it becomes 2.1 times 2.
Yeah, I did it backwards.
What do you mean backwards?
Number 54.
Right.
I switched those to kind of calculate.
Oh.
I think on number 54, the answer is like square root of 2.
Yeah, let's do that one. What's 54? Log
Log 16.
of A
Yeah.
equals what? Right.
You should find that.
So we got 4 to the 2.1 we know is A. Right? And so this is 16 to the what makes A. Right? Yeah, so then you could make this 4 squared to the what? Right? So that'd be 4 to the 2x, I guess you might say, is equal to 4 to the 2.1, right? So x has to be half of 2.1. 1.05, whatever. So it's just a matter, when you've got these different bases, the key is when you've got these different bases is to write them and then, adjust those bases so that they agree, and then you can compare. So that's kind of what was going on. Okay. All right, let's go to the story problems. Now, the thing is, a number of people were in here this morning. Will came in, Emily was in here, getting in here and whatever, asking some questions early, which is great, because even though we may go over some of them, we're not always going to go over all the problems. It just depends how critically important it is and so forth. But even then, even if we do go over it again and you come in the morning and got it, you just hear it a couple different times, it's so much better. The whole point of Appendix G is later on, we're going to be doing some calculus to some functions. The calculus we do has to do with increasing, decreasing. We're going to talk about some of those terms today. Finding maximums and minimums is a big deal in calculus, okay? But before you can find the max of a function or the minimum of a function or where a function is increasing or where it's decreasing, you've got to be able to write the function. You've got to be able to set up the function. And so the calculus doesn't do you any good if you can't do the algebra of setting up the function. That's what these problems were about. And they're not easy. I mean, you think back to Algebra 2, probably the hardest part of Algebra 2 is when you do the story problems, you got to set them up. That's the hard part. So number 4, now I skipped number 2, so maybe we should back up. Let's actually look at number 2. Number 2 said you got a cube. The cube is what by what by what? That's the tank, right? But now that's the empty tank, right? Okay, why? I wonder if I'm a little too far away from my computer. It's got water in it, right? Water's flowing into this tank, right? And so what's the volume of the water? What by what by what? 10 by 10 by however deep it is. So the volume of the water is 100 deep. Now, so what you got, but the real key to these problems is you got to understand the words, right? Because on a quiz, you come up to me, remember what I told you about quizzes, right? You come up to me and you say, I don't understand what this is saying. I'm going to say, that's part of the question, is understanding what it's saying, right? We've got to know the language. We've got to know the language, okay? So when it says write V as a function of D, this is what they mean. V as a function of D means V equals with D's in it. That's what it means. V is a function of D. The function you're used to is f of x. That's f as a function of x. That's the language, okay? So we had to write that. Then what they want, what's the domain? Right? Well, what's domain mean? Your input values. I'm glad you said that, because not all functions are going to have x in them, right? So you're going to hear me use the word input and output a lot. Well, what that means is x and y, right? But we're going to use different letters. We'll have different function names, right? And so I won't say x value very often. I'll say input value, okay? So domain is the input value, which the input value here is d, right? So it's what are the possible d values, which means what's the littlest d can be, what's the biggest d can be, and are there any numbers d couldn't be, right? That's what you think of on domain. So what's the littlest D can be? Littlest D can be 0, right? Could be empty. And then what's the biggest? Or anything in between, right? And we got our new function notation for that. What's the range?
0.
Well, but what values? They're the possible outputs, which in this problem is volume, right? So what's the littlest volume we can have? 0. What's the biggest volume? If it's full. Okay? Right? What else? Did you ask anything else on that one? Okay.
Formula for D is a function of D.
Oh. What's that?
B divided by 100.
Right? Just the language. Just function of D. D is a function of B. Just means D equals, and then V's in it. Okay? So that would be that. All right. Back to this one. So now we got the mugs. Now, here's the calculus problem. If this was chapter 4, the problem would have been this. The problem would have said that when you manufacture these mugs, did I write this wrong? This is supposed to be a 50, isn't it?
Yeah.
When you manufacture these mugs, if you sell them for $1, you can sell 1,000. But for every penny you reduce the price, you can sell 50 more. And the mugs cost you 60 cents each to make. What price should you sell them at to get your max profit? That'll be the question. Right there. And then you'll have to do all of the parts A, B, and C, and D that they did for you, right? So what they're doing here is just trying to get you to see where they came from, okay? So we can sell 1,000 mugs. So N is the number of mugs, right? In terms of X. And they told you to let X be what? Number of price reductions, right? Now, usually in a problem like this, X is how many we sell. X a lot of times is how many mugs. But this case, they say it might be easier to do, let X be the number of price reductions. So N is going to be in terms of X, number of price reductions. Okay, so N is the number of mugs we can sell. Well, we know we can sell 1,000, but we'll add on 50 every time we reduce the price. So X is each price reduction. So X is a 1, that's 1 price reduction. X is a 2, 2 price reductions. We'd sell 100 more mugs, and so forth. So it's pretty easy to see why this is the number of mugs, right? Okay, this is the profit. I put a little p. This is a profit for 1 mug. Well, each mug costs us 60 cents, so we got to take that off our profit. But we're going to sell them for $1. So basically, we get 40 cents. So you could have done it that way. I probably would have set it up that way. But, because this will simplify to this, won't it? It'll be 0.40 minus 0.01x. That's actually what it's going to simplify to. Okay? We're going to make 40 cents on every mug, minus the penny that we might reduce the price, right? So if we have 1 price reduction, we'll lose a penny, we'll only make 39 cents on a mug. If we reduce the price another penny, we'll only make 38 cents on each mug, right? So what you have is more mugs. If you make them cheaper, you can sell more, but you're not getting as much, right? So these two things are conflicting. Well, that's the way the real world works, honestly. That's a huge business thing. Hey, if we make this cheaper, we can sell more of it. But we make it cheaper, we might not make as much on each one. So where does that balance out? Where's that magic price we should set to sell the most, right? And but to make the most. I mean, that's the bottom line, is to make the most. So that's the calculus problem that we would want. Okay, so this is the profit. So $1 minus the price reduction, so that's what we'd sell it for, 99, 98, whatever, minus the 60 it costs us, profit on 1 mug. So what's the total profit? Those two multiplied together. So that one times, I'm going to write this one. Now, if I was setting this up, think about how, if we'd had to set this up from scratch, what we'd have done is we'd have said, okay, I want to find the max profit. So what would be my profit? Well, it'd be my number of mugs, and so I probably would have written something like this up here. I'd have written down number of mugs times profit per mugs. And then I just said, well, how can I get my number of mugs? Well, I can sell 1,000, plus I would add on 50 every time I reduce the price. So that would be your thought process as you build this equation. Okay? All right. And then what did they say? Did they want a domain and range? They just want the equation. And then what, find the best price, they said? Yeah. So what they mean there is just graph this, right? For now, because we don't know what the calculus, we don't know how to do the calculus. So all we can do is just graph this. So you graph it, it's gonna be an upside down parabola. That's all you have to do is trace it there. Did they do that? What do you get? So you got x equals 10?
Yeah.
So you graph it, the max is at x equals 10. Well, what does that mean? 10 price reductions, right? Because x was the number of price reductions. So 10 price reductions means 10 cents off, so 90 cents would be the best. 90 cents would be the price you should sell. Okay? Now, yeah, so anyway, all right, let's move on. Let's go to 20 first. Okay? Now, here's what I got. What they wanted me to get a cost. What did it say exactly? Find the cost per mile per hour. Was that it?
It's just called.
No, it's find a formula for the cost per mile as a function of speed, right? So cost per mile. So we want to end up with dollars per mile. That's what I got out of that. When I saw that, it said find the cost per mile as a function of speed. Well, what's that mean? That means over here I should just have V's in, right? As a volume of speed, I should just have V's. Well, that makes sense because the only thing else I have there is V's. So that'll work nice. But that's what I'm looking for. So I'm going to call it C for cost and V for the speed. And I want to end up with dollars per mile. So I want to look at these things. These are the things they gave me. $1.50 per gallon for gas. V is my miles per hour. $15 per hour for the driver. And this is how many miles per gallon I get. So I need to put these together somehow to get dollars per mile. Now, doesn't it look like these two could go together pretty nicely? And this is often a strategy in these problems, is look at your units and see how you can put the units together to get dollars per mile. So what am I going to want to do with this? Well, if I take $1.50, which is dollars per gallon, right? How can I get dollars per mile out of that? Well, I'm going to want gallons to cancel, right? Well, how can I get gallons over miles? How about I invert that? Right there. Won't that give me dollars per mile? That's for the car. The gas was $1.50 a gallon, and it gets this many miles per gallon. So all I have to do is invert that, right? And that'd be dollars per mile. Plus, I got to pay the driver. So don't these two go together pretty well? 15 would be dollars per hour, and I want hours to cancel hours, so I can end up with dollars per mile. So how can I get hours over miles? 1 over V. 1 over V would give me hours over miles. So there it is. So 150 times 7, what's that? 1050 over 180 minus 2V plus 15 over V. That would be my cost in dollars per mile as a function of speed. Okay? So it looks like as my speed goes up, this is probably going to get bigger, right? These are going to get bigger, so the faster I go, the more it's going to cost, right? Because the mileage is worse. All right, anyway, let's go to number 11. All right, number 11 says, this is always one of my favorite problems. We'll reference this many times later in the year, but you got this guy stranded in the snow, and he's going to, get out his calculus and sit there and figure out exactly where he should walk, so he can get there the fastest. But he's got options. He can either go straight north 3 miles and then this way. What's wrong with going that way? What's the disadvantage of going that way? It's longer. What's the advantage of going that way? He walks more on the road. And why is that an advantage? Because he can go faster on the road, right? On the road, he can go how much? 4 miles per hour, right? And in the snow, he goes 3 miles per hour, right? So then, of course, the other option is to go straight to the thing, and that's shorter, but slower because it's in the snow. So, or then he can do something in between. So that's why I've drawn this line here in between. Okay, so what did they say? They said write a function for the time in terms of R, which was how far he walks on the road. Well, if he goes this path and then to here, wouldn't this be R right there? Okay, now I want the time it takes him. Well, so what I need is the time in the snow plus the time, and this is another one of those when I look on your paper and I see it with an answer, it's like, okay, come on, it's an odd one. I kind of know where that goes. You've got to have a picture. You've got to have some other stuff here. So it's a time in the snow plus a time in the road. Well, what's a time? Well, what's time? Distance equals rate times time, right? So time would be his distance divided by his rate. Distance divided by his rate. Well, what's his distance? Well, what's his distance here? What's his distance here? I don't care about this distance. It's R that he's walking, but I need this triangle. So what would this be here? This would be 6 minus R, right? And I need that because that's the only way I can get this hypotenuse. What would this hypotenuse be? 6 minus R squared plus 3 squared, which is 9, and then the square root of all that. And I don't even need to simplify that. We can throw it in our calculator just like that. So this is his distance in the snow. How do I get the time in the snow? Divide it, right? Take his distance, which is square root 6 minus R squared plus 9, and divide that by his rate in the snow. Plus his distance in the road, which is R, over, there you go, you're done. Okay? But imagine how you had to think through that, right? You had to think of your possibilities, you had to label it, they told you what R was, but you have to label it, you have to get some expressions for that, then you have to think what is time? Time is distance divided by rate. They gave you the rate, your picture shows the distance, you put it together and there you go. And you got a time equation. Now, what would the logical use of that be then? Maximum? Minimum. When we want the shortest, right? We want the minimum time, right? So we did the mud problem where we want the maximum profit. Here we want the minimum time. So which way should go? If you graph this, I think it looks like this, right? It looks like this. It's not a parabola, but it has kind of that shape. And there's going to be some R value where they give him the minimum time. So there's some place there that he should go to, but again, it's not a very realistic problem. But here's an example of here's another classic calculus example that would be very similar to this. Let's say you got a river. Okay, let's say you got a river here, and you want to lay some cable that you need to get over to this, over here, some electrical cable or whatever. Now you got an option to go underwater, and you could go straight there, but it's a lot more expensive to put it underwater. Or you could go across and then on land here, underwater here, and then more on land, so you go shorter under the water where it's more expensive, and then over here where it's cheaper on land. So you can do that, and then, so the idea is calculate what would be the cheapest, where should you go for it to be the cheapest. And that's something that would make sense, because you could actually make that calculation, plan where you want to do it, and go. So it's a similar kind of scenario. Okay? All right, let's get your notes out then, and let's move on here into chapter 1 in our book. So if you turn to...
I don't think your triangle makes sense.
Which triangle?
Because of the directions.
I think that's what it said. Let me.
It said that the point was southeast, and the way you had it was
I disagree with you. It says.
Because it's 3 miles south and then 6 miles east. The way you had it was 3 miles north.
No, but it says the station is east. Okay, here's what it says.
And the road is going south.
Okay, no. Okay, here's exactly what it says. It says, you are 3 miles due south of a major highway. Okay? So you are 3 miles due south. Right? The nearest service station on the highway is 6 miles east of your position.
You are 3 miles south.
It says you are 3 miles south of a major highway, and the nearest service station is 6 miles east of your position on the highway. So it's 6 miles east of your position on the highway. Yeah, no, you're right. I mean, it's a, let me read it exactly. The nearest service station on the highway is 6 miles east of your position. So you could go this way 6 miles east, but it's, so I think that's what it was. But, and that's one of those that, yeah, if it was a quiz and you drew it going the other way, like that way, is that what you did?
No, I drew the 3 I thought he was the
Over
highway
here.
was south of him.
Oh, which would be the same, essentially, right? So if it didn't matter, I probably wouldn't make a big deal about it. If I thought there was going to be some confusion on the quiz necessarily about it or whatever that would make a difference, then I might give you the picture. You know what I mean? All right. So anyway, chapter 1. So page something. 1. Hey, how about that? Page 1. Makes sense. All right. So now we're focused in on the quiz. I still haven't decided on the quiz. I think I told you yesterday. What day did I tell you yesterday? Wednesday. I'm still not sure if it's going to be Wednesday or Thursday. Right now, I plan on Wednesday, but that may change. So we're going to talk here in the big emphasis, the huge emphasis here in this first quiz is functions. Functions. Calculus is about acting on functions. Everything we do deals with, almost everything we do deals with functions, okay? And so we got to understand what that means. So when we're talking about functions, we're used to functions being like the ones we just got done setting up. Expressions, x squared, sine x, e to the x, right? Those are basic functions. But we can also have functions as graphs. So inputs and outputs, domain and range. So the first thing we want to do is talk about the language of functions, all right? And notice the title of this section is Functions Calculus Style. Okay, so what is it about functions we're going to really need to understand and know for this class? So they give an example. Hot days on the Kansas prairie generate strong updrafts and downdrafts in the gondola of a hot air balloon. 2 instruments monitor the course of an 8-minute period. An altimeter shows the altitude, and a rate of climb meter shows how fast the balloon rises or falls. And here are these graphs. So if we look over page 2, then we've got these graphs right here. Now, picture for a minute this hot air balloon. Okay? 8-minute time period. One's the velocity, one's the altitude. Now, in your mind, if you're picturing this hot air balloon traveling over these 8 minutes, what are you picturing? Are you picturing this kind of a thing? Floating this direction? You're shaking your head no. What do you picture?
Like if I was looking up, it would just be going flat.
Just like this?
Yeah.
Except this is its altitude, isn't it? So isn't it going higher and then coming back down? Wouldn't it? Based on this graph. Okay. But I guess what I was getting at was, would it have to be going like this? Did anybody picture this balloon just going up and down like this? I guess it's probably not. I know the first time I read this problem, I did not think of that. I just thought this balloon kind of floating over the perimeter, right? But all this graph tells us is how high it is. And all this graph is telling us is its vertical velocity, right? Up, positive, down, negative. That's why some of it's below the x-axis, some of it's above the x-axis, right? Okay, so really all this is talking about is the balloon going, it's up and down motion. Okay, so important to understand it. All right, so these are both functions, right? You know the old vertical line test, right? Any one input can only have one output to be a function, right? That kind of stuff. So we can have functions that are not equations, that they're just graphs, okay? So like this example here. Now there are some interesting things on this that we want to look at. And so on page 2, they talk about some of those things. The graph of V you know, if we look at, or excuse me, if we look at this graph, when this graph, what can you tell me about when this graph is going up? What do you notice on this, till a little past 1, what can you tell me on this graph? What's important about this graph when this graph's going up? What's the important feature of this graph when that graph's going up? Yeah, it goes down, but it keeps going down too after that. So I don't think that's important. It's what? Well, at this point it's at 0. But what about here before it? What's important about these dots here when this graph's going up? I'll give you a hint. Here's another place where this graph is going up. And that's a little after 3 to 5. Little after 3 to 5. Positive. That's what's important. When this graph is going up, doesn't this graph... Now, let's talk about that. This is really important. When she says this is positive, what are we talking about? It's y values, right? When we talk about a function is positive, we're talking about its output function. It's y values, right? The y values here are positive, the y values here are positive, and a little past 7 until the end, these y values are positive. And what's this graph doing a little past 7 until the end? Going up. So every time this graph is going up, this graph, now, but that makes sense because positive velocity in this problem is when it's going up. Negative velocity is when it's going down. So when this graph is going down, here to here, this graph is negative, right? Below the x-axis. When this graph is going down over here, its velocity is negative, right? So when we talk about a function, so we want to talk about the words increasing and decreasing. When we say that, we're talking about the graph going up or going down. When we talk about the graph being positive or negative, we're talking about it being above the x-axis or below the x-axis. And of course, it's 0. You mentioned it's 0. What happens every time this graph is 0? Little past 1. It's at a peak, right? A maximum or a minimum. We're going to have names for those. We'll talk about more in the next section. Okay? All right. Fast or slow? Fast or slow has to do with how steep. Now, you notice, when's this one the fastest? When's this going down the fastest, the steepest? Right in here somewhere, maybe? Going down pretty steep. Then it kind of levels off. It's kind of level here. Then it's going down the steepest, right about 6. What's that correspond to over here? Oh, at the bottom of that one, right? The minimum of that one, because these are the velocities, right? So the farther you get away from 0, the faster this thing's going, right? So this is where I was talking about like acceleration. You got to be careful with acceleration. You can't just say if the velocity's decreasing, then something's slowing down. Let me say that again. If somebody said to you the velocity's decreasing, wouldn't you picture something slowing down? If I said my velocity is decreasing, right? When you picture something slowing down, that's not true. If your speed is decreasing, it's slowing down. Speed and velocity aren't the same thing, right? Because velocity can be negative. Speed's always positive. Velocity has direction. So look at my velocity graph. Right now, what's my balloon doing right here as I go this way? What's the balloon doing? Going what direction? No. Because what is this graph I'm pointing to? I'm pointing to the velocity graph, right? So right here, the velocity is, what do we care about? I don't really care right now that this graph's going down. What I care about that this graph is positive. And what's that mean the balloon's doing? Going up. So right now, the balloon is going up, right? But what's the balloon doing right here? Huh? It's stopped right here, right? It's going to start going back down, but right now it's stopped, right? So the balloon is slowing down because its velocity is like 800, 700, 600, 500, 400, 300, 200, 100, right? The balloon is slowing down and stopping right here. The velocity is decreasing. So it is slowing down. But isn't the velocity still decreasing right now? But what's it doing? Going down, and it's also speeding up, isn't it? Because the velocity is like negative 100, negative 200, negative 300, negative 400, negative 500, negative 600, right? It's going faster and faster coming down, right? So it's going faster, 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 faster until there, and then all of a sudden now it's still going down, right? Still going down, right? The balloon's still going down because its velocity is like negative 2,000, negative 1,500, negative 1,000, negative 800, negative 700, negative 600. Still going down, but it's what? Slowing down. And right here, what's it doing? Stop, because it's zero, right? And of course here it's going down, 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 down until right there it stops. Now it starts going back up. This graphs its altitude. It's up and down. This graphs its velocity. So we're really going to have to pay attention to what is the graph represent. What do those values mean in the situation when we're talking about a function? Okay, so anyway, and we also talk about slope. We said it's going the fastest here because that has to do with slope, right? How steep, so we talked about that one. Okay, look at the top of page 3. You got a table. That could be a function, right? It's got inputs. What are the inputs at the top of page 3? Not what are they? What? Give me units. The inputs. What would be the x, Jesse? The year. The year would be the x. The top row would be the x, and the y would be people. So domain would be year, range would be the people. If you plotted that, you would just have some dots, right? A lot of times, sometimes you don't connect the dots, right? They try to a little bit there below, but sometimes a function is just a series of points, right? If you have a table, you might not know what's in between those points. Go to page 4. Here's another function. Okay, the top of page 4. We got another function. It's just a table of values. So now let me ask you some questions about that k function right there. Look at that function, top of page 4. If I ask you what is k of negative 2, what would you tell me? K of negative 2. Negative 9, right? Negative 9, right? That's yeah, when an input of negative 2, we have an output of negative 9. If I ask you the domain of that function, what would you tell me? What's the domain of that k function right there? Negative 3. No. If you told me negative 3 to 4, then that would include 1.7 and 1.8 and pi and all those numbers. The domain is not negative 3 to 4. What is the domain? Negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. That is the domain, right? And the range is those values, right? When you have a table, that's all you know. So what if I ask you for k of 7? What would you say if I ask you what is k of 7? Oh, that wouldn't be the right language. Bingo. Undefined. Now let's think about that a minute. When do you usually use undefined on a function? Give me an example. Dividing by 0. So if I had the function f of x equals 1 over x, and I asked you for f of 0, you'd say undefined, because 1 divided by 0 is undefined. Okay? If I said f of x was equal to square root of x, and I asked you for f of negative 3, what would you say? Undefined, square root of negative 3, over the real numbers, right? You could get into i's and imaginary numbers, right? But let's just say we're doing real numbers, which we are in calculus most of the time, at least in our calculus. And so if we put in a negative 3 there, it'd be undefined, because there is no. So, but what does undefined really mean? What undefined means is this function does not have an output value for that input value, right? That's what undefined means. So in this problem, k of 7, this function does not have an output value for an input value of 7. It's undefined, right? So it's the same thing we've always said with undefined, but we kind of get it in our heads that it's just dividing by 0 is undefined or square root of negative is undefined, but that's what undefined means. So if I ask you for k of 7, you say, oh, for that function, it's undefined. Okay, there's not a value. All right, piecewise function. Critical thing here. If you haven't been paying attention, if you haven't woke up yet, now's the time to get woke up, because I promise you, this will be on the quiz next week. I promise you there's going to be a picture that looks like this, and you are going to have to write the equation of this function, okay? Now, let's don't look in our books anymore because they have the answer there already. Let's work through this together. This is called a piecewise function. Now, this is not a hard concept. A piecewise function is just a function that's defined in pieces. How hard can that be? This one has 4 pieces. It's got a line, it's got a half of a circle, it's got another line, and it's got a third line. And all we have to do is write the equation of each of those pieces. Okay? We just have to write the equation of each of those pieces. So the way we do that, and let's just call this f of x, equals, and then we have a big curly bracket, and then we're going to have the 4 pieces. Okay? We're going to put the 4 pieces right there. So let's do the lines first, because those are the easiest. All right, and the only thing I'll ask you to do on this is just like this one. Lines, and parts of lines and parts of circles. Those are the only 2 things I'm going to have you do. Okay, so let's do the lines first. Those are easy. Now, we already talked about line equations. Y equals m times x minus the x point plus the y point. Now, every time on our first quiz, people screw this problem up, and I can't believe they will. I can't believe you would screw this up when I just told you it's going to be on there. So between now and the next quiz, you better be practicing this and coming in and talking to me and seeing if you got questions, and right? Because I just told you, I don't always tell you exactly what problems are going to be on there, but pretty much just did right here. Okay, so let's do this line. Well, what do we need? Need the slope. So it goes down 3 over 2. So that's going to be y equals negative 3 halves x minus, I need a point. What point we want? Let's take that point right there. Negative 3, 0, so it'll be plus 3, and then plus, oh, that's nice, plus 0, right? That's good. That's a good one. Picking that one, won't have anything over there. Now, should we distribute that? You can, but you don't have to. You don't have to. Now, how do we write that over here? That's our first one, so I'm going to put it up on the top. Tell me what to write. No. I set you up for that one, Max. Thanks for volunteering, though. We're not going to write y equals. Why not? Because we already have y equals right here. Right? This is y equals right here. So we're going to write negative 3 halves, parentheses, x plus 3. You want to write the plus 0, you can. Okay? So we got that one, and that, but there's another part of that we got to do. Let's put a comma, because that line that we just wrote goes all the way through here like this. Ours doesn't do that, right? Ours only goes from what x value to what x value. It goes from negative 5 to negative 3. So I'm going to put a bracket, and I always go left to right. And so that piece, I got to tell it. I've got to tell in my function what piece, how big is that piece. So I want that line, but only from that x value to that x value. All right, now let's skip over the circle for right now, and let's go to this line. So I need the slope. What's the slope on that one? Looks like the slope is 1. And then x, and let's pick this point right here, 1, 0. X minus 1 plus 0. That's easy. So what am I going to put in here? Now let's put it, it goes in the 3rd slot. I still have that circle to do. So let's put it down here. So just x minus 1. So I got y equals x minus 1. And then that goes from where to where? 1, 2, 3. Okay? And then let's do that last piece of line. That'd be y equals, what's that slope? Negative 1. And then I got the point, what, 5, 0? So x minus 5 plus 0. So that's going to be y equals negative 1, parentheses, x minus 5, which, again, you could distribute that if you want, if that's bothering you. Comma, and then what? Okay, now a little bit of a technicality here. It hasn't been an issue so far because we skipped this one. We can't include 3 on this line and then also include it on this line. So I don't care which one, but if I included it on this one, don't include it on this one. And then I do want to include the 5 at the end. Now, here's why. Because sometimes you get piecewise functions that look like this. Sometimes you get piecewise functions. You might have a piece of line that comes in here like this, and then the other piece of line takes off and goes like that, right? So in that case, you definitely would not include this endpoint, and you would include it on that one. But on this one, each piece begins where the other one left off, so it's not really an issue. Okay, but sometimes we'll get piecewise functions that do that. Okay, so you write the equation for each piece. So 3 of them are lines, and then the last one's a circle. So we got to talk about a circle here. All right, so let's go. I'm not going to have room here, so let's do the work on the board over here. So you have got to memorize this. You've got to know that this is the equation of a circle. Okay, you've got to know that that's the equation of a circle by next week. Okay? And the hard part of that is it's not y equals. Right? Now, if you would like to solve this for y and then memorize that, that's okay. Or I think it's probably easier to just memorize this, plug in your numbers, and then solve for y. So, what do we need? We need the center of the circle. That's what h and k are, right? H and k are the center. If you need to put that down, h and k are the center. And of course, r is the radius. Right? So what would my equation be here? It would be x, where's the center? -1, isn't it just right there? Because that would be 2 this way, 2 that way, 2 that way, right? That'd be your radius. So -1, 0 is my center. Okay? So that would make this what? X plus 1 squared plus. Now, I'm going to do this on this problem because you're not always going to get so lucky to have 0 there. And then, so the y squared is easy to solve for here. Let's do it this way, because that way if later you get one where there's a 1 there or a 2 there, you'll see how to handle it. So let's go ahead and write it out this way. And then what's the radius? So this would be 4 right there. Okay, now I need to solve this for y, right? So how can I get the y by itself? Let's subtract that. So y minus 0 do us no good to FOIL these out. There's no need to FOIL these out. So 4 minus that quantity, right? Then what? Square root. Now when you do the square root, you got to remember that it's plus or minus. Now, another thing, I know some of you are itching to do this, and I'm not going to make you admit it, but when you do the square root of this, can you do the square root of 4 and get 2 and do the square root of this and get rid of the parentheses? No. Okay, simple little example. What's 9 plus 16? 25. What's the square root of 25? 5. What if I do the square root of 9 and the square root of 16? 7, not 5, right? You cannot, when you have a sum or a difference, you do the square root. You can't do the square root of each one separately. Right, so you can't do the square root of 4 and the square root of that. You can't do it. Can't do it. You just have this big mess like this. All right? Now, plus or minus. What's the plus or minus mean? It's a circle. Notice how we only have half the circle here? What if we had that piece? What if we had both pieces of the circle? What if we had both pieces of the circle? Wouldn't be a function. It would fail the vertical line test, right? So if you're going to have a circle that's a function, you can only either have the bottom half or part of the bottom half. You might just have a quarter circle, right? But the quarter circle, we would define that by this here. So if you've got the bottom pieces of the circle, use the negative. If it's the top half of the circle, it's the positive, right? So if you're going to graph this if you wanted to, for the heck of it, graph it on your calculator, right? You would have 2 graphs. You would have to graph the positive square root, and that would graph the top half of the circle, and graph negative square root would give you the bottom half of the circle. Well, which one do we want? We want the bottom half, so we want to keep the negative. Okay, then we would add the 0 to both sides. which I usually just put in the front, to be honest with you. So I'm going to add the 0 over. So you understand that if you had a 0, if you had something other than 0 there, like a 2 or a 3, now you would add that 3 over, add that 2 over, and just put it there. And there's your y equals. Okay, so now what goes into here? What goes in here, right? Now, yeah, 0 minus, and I won't put it this time, but you can put the 0 minus, that's fine. Square root of 4 minus quantity x plus 1 squared. I think they didn't simplify it out either. They've got the same thing. Okay, and then comma, so that's the bottom half of that circle. And then that goes from where to where? -3 to 1, what do we put? Not included on both of them because we've already included them on those other ones. Now, normally you probably would have, if you'd have just went left to right, you'd have included this one, not included this one, but maybe included the one, then not included the one here, but included the 3. You know, so you might have done it that way. But it just ends up being that way because of the order we did them in, right? But it doesn't really matter. Okay.
On function 4, if you keep that -1 there, do you care if we just put a negative sign?
Yeah, no, that's fine. If you just do that. Absolutely. Same thing. Absolutely. Okay. All right. So Garrett, now there's one of them on your homework. There's actually 2 of them. There's one on your homework where you do this, and there's one on your homework where they give you the piecewise definition, and then you draw the graph, and you just draw the pieces. Okay. Now, I was saying a minute ago that what if we just had a quarter circle? Like what if this wasn't even here? What if this piece of the circle wasn't even here, right? What if this was just empty, right? Well, you would do all the same stuff. You would say, okay, we still got a circle, center would still be here, still have radius 2, right? You would do all this same stuff. You would put it in here, but instead of going from -3 to 1, you'd go -1 to 1. Right? You just go -1 to 1. So there's not different equations for half circles and quarter circles, right? I mean, there's just equation for a circle, right? And the plus or, this is for the whole circle, but when you get down to here, you get the plus or minus, that's for the top and bottom half. Well, if it's going to be a function, you can only have one. You either have the top half or bottom. You can't have part of the top and part of the bottom. If you have part of the top and part of the bottom, it's not a function, right? It's not going to be a function. So to be a function, it's going to either have to be the bottom half or part of the bottom half, or it's the top half or part of the top half. Okay, so that is going to be in there for sure. So they went through that on that page. Okay, and they give that to you. All right, then there's a couple little things with some story problems. We won't worry about that right now. Go to page 6. So it talks about what is a function, formal definition. So again, just to summarize, we can have functions given to us a lot of different ways. One way with an expression, if middle of page 6, there's what we're used to with functions. We could just give a function described in words. We could give a piecewise description of a function. We could give a graph for a function. We could have a table for a function. Those all are functions, right? As long as in the table you don't have 2 different x values giving you the same y value, right? Again, that would fail that vertical line test kind of thing. All right, and then domain and range, we've already talked about that. So domain is your input values, range is your output values. Now you might be asked to do that for a graph. What about this graph? What about this graph here? Let me erase this, all this mess. What about this graph? What's the domain on this graph? -5 to 5, right? What's the range? Now let's go little to big. Always go little to big when you give your range and domain. Not -1. Isn't it -2?
Oh, okay.
-2 to 3. Right? -2 to 3 would be the range. Range are the y values. The y values go from here up to here. Right? Those are the range. Domain this way. Range is the other way. So range are the y values. Y values go from negative. They give an example like shining a spotlight, a headlight. I think if you look over on the next page 8, middle of page 8, like if you shine the light from both directions on your graph, it'd be the shadow on the y-axis would be your range. You know, I mean, so yeah, you got y values here, 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 all the way down to here. If you shine the light down here, it would just go, just go through. Kind of the way things arrange. But all right, we also have what we call the natural domain. So sometimes you get a problem. Sometimes we get a problem when we say this. Let's look at the function sine x from 0 to 2 pi. So what they've done is they've just given you the domain. They only want you to look at it from 0 to 2 pi. So they've given you the domain. A natural domain is when they don't give you the domain, you just figure it out. So for example, if I give you f of x equals square root of x, what's the domain? What's its natural domain? What can you plug in for x? Positives or 0. So x greater than or equal to 0. Or you could do 0 to infinity. Wouldn't that be the same thing? So the natural domain of square root of x is 0 to infinity. Okay, that kind of thing. So so functions have just their natural domain that they've asked about, but sometimes we fix a certain domain too for a function. Okay, all right, so your homework is the 1.1 homework questions. I'll let you get started on that to work. I gave you this yesterday, right, the scavenger hunt? So that's due to hand in on Monday, so don't forget that also. Okay, so 1.1 homework questions and that scavenger hunt for Monday. So what you're gonna see in the homework, you're gonna start getting used to this book. It's not your typical kind of old algebra, kind of like that Appendix E. To me, Appendix E was like the typical old math assignment. Just a whole bunch of problems, There's gonna be a lot more word type problems, not story problems to speak of, but there's gonna be a lot of questions in this assignment that's gonna be domain and range, reading off of some graphs. Just these things we've talked about functions. There's going to be that stuff with piecewise, looking at that a little bit. Okay, so getting used to function language. What's that?
Is that like above sea level or above ground for that height? Because 6,000 feet.
I think I would say that's sea level. Yeah, I would say that's sea level. But I don't know. Does it go down to?
Yeah, it asks that.